Hi everybody, this is lesson 2.6. All right, so we've been talking a ton about limits, and today we are going to continue with that and discuss this notion of continuity. So we'll be discussing what it means for a function to be continuous. But first, our mathematician of the day is Hypatia, who is my personal favorite mathematician. She was a 4th century philosopher and mathematician who was perhaps the world's first greatest female mathematician. She was killed by a mob of Christian zealots after getting too involved with politics. So that kind of stinks. I'm really glad that I don't live in the 4th century. Yeah. And did you know that Stonehenge, which is considered a physical and mathematical marvel, was built in the 18th century BC? Isn't that amazing? How did they get all those big rocks moved? It's just incredible. Okay, so again, we've been talking about limits a lot, and today we're going to talk about a new thing, which is continuity. So we have this definition for continuity. A function f of x is said to be continuous at the point a if we have this true. We need the limit as x approaches a of f of x to be equal to f of a. If this is true, then our function is said to be continuous at the point a. In order for f of x to be continuous at a, we need the following three conditions to hold. We call this our continuity checklist. So we need three things. First of all, we need f of a to be defined. If f of a is not defined, then it is not continuous. Secondly, we need the limit as x approaches a of f of x to exist. And lastly, it has to satisfy the above definition. So we need the limit as x approaches a of f of x to equal f of a. So let's use this continuity checklist in order to look at example 1 and see where I am discontinuous. So it looks like at the point -2 here, my limit as x approaches -2 looks like it's the point 1, but that is not where my point is defined. So I am discontinuous at x equals -2, x equals -2. This breaks the third rule. My limit is not equal to the function evaluated at that point. So breaks rule number 3. Because the limit as x approaches -2 of f of x is equal to 1, which is not f of -2. Okay, let's look at the point -1. If I look at this point -1, I see that I have two empty circles there, which means that neither at this point or at this point is my function defined. So I'm also discontinuous at x equals -1. This breaks rule number 1, since I'm not defined there. And it breaks rule number 2 since the limit does not exist. I have a separate right-hand limit and a separate left-hand limit. So my limit doesn't exist, again, because I have a separate right and left limit on that point. We look good up into the point 1. So what's happening at x equals 1? Well, it looks like I have some sort of vertical asymptote there, which means that my function is not defined. It also means that my limit does not exist, since I'm going up towards infinity from both points. And it breaks rule number 3, since I can't actually equal infinity. So at x equals 1, I am discontinuous because I am not defined. I break rule number 3. Oh, excuse me, rule number 1. Rule number 2, and rule number 3. I'm not defined there since I'm going up towards infinity. My limit does not exist since I'm going up towards infinity. And I can't actually evaluate the function at 1, so that makes 3 invalid as well. All right, let's go to example number 2. We want to use the continuity checklist to determine whether the following functions are continuous at this given point x equals a. So let's look at the first one. F of x equals 4x squared minus 3 over x plus 2, and we want to check what's going on at the point -2. So first of all, this is a rational function, and we learned last lesson, I think, that if I have a rational function, we can simply plug in this point. So the limit of a rational function is simply the limit of the top divided by the limit of the bottom. That's what we learned. So I'm going to plug in this point and see what happens. So f of -2 is equal to 4 times 2 squared minus 3 over -2 plus 2. Well, we have a problem here because this becomes 0, and if my denominator is equal to 0, that means that I have a vertical asymptote there, which means that my limit is not defined, right? I'm either going towards positive infinity or negative infinity, so I am not continuous at the point -2. Not continuous at a equals -2, since f of -2 is undefined. I have a vertical asymptote there. And then I want to look at the same function at the point -1. So if I have a rational function that does not equal 0 on the denominator, I am always continuous, right? Rational functions are continuous except for when my denominator is equal to 0. And if I plug this point into the denominator, I can see that it's not equal to 0. So this is continuous, since all rational functions are continuous as long as our denominator does not equal 0. This is the same case with polynomials. Polynomials actually are always continuous, so we don't have to worry about polynomials being continuous or not. All right, next we are going to move on to some continuity rules. So I assume that the functions f and g are continuous at the point x equals a, and then the following functions are also continuous at x equals a. We assume that c is a constant, just a number, and n is greater than 0 and is an integer. So if f and g are continuous at the point a, then so is f plus g, c times f divided by g, as long as g is not equal to 0. Also, f minus g is continuous at the point a, f times g is continuous at the point a, and f of x to the power of n is continuous at the point x equals a. Our next thing is a theorem, which we've already talked about in the previous example, but any polynomial function is continuous for all x. That's because we don't have any places in polynomials where my function is undefined or where I have a jump discontinuity or anything like that. I just have a fluid, solid line that is continuous everywhere. And a rational function is continuous for all points for which the denominator is not equal to 0. Again, we saw this in our previous example. I want to use the theorem that we just learned to evaluate this limit. So I'm going to use this rule right here since I'm raising a function to a power. So I'm raising this inner function to the power of 5. And I can do this as long as my inner function is continuous at the point x equals 1. Well, let's look at the denominator here. I have x to the power of 6 plus 2x plus 7. Is this ever equal to 0? If we were to look at the graph of this function, actually it is never equal to 0. So we're good. Because of this 2x plus 7 business, basically this function looks something like this. I'm never equal to 0. So the function, the inner function, x to the power of 4 minus 3x plus 5 over x to the power of 6 plus 2x plus 7 is continuous everywhere. Since our denominator never equals 0. And because our inner function is continuous, I'm going to use this rule right here that tells me that my function raised to the power of 5 is also continuous. So I can just plug in my limit point, x equals 1. So this function, x to the power of 4 minus 3x plus 5 over x to the power of 6 plus 2x plus 7 is also continuous. I'm going to call it by this theorem right here. So I can simply plug in our limit point x equals 1. So we plug in x equals 1. Whoops, I forgot my 5 here. When I plug in x equals 1, I get 1 minus 3 plus 5 over 1 plus 2 plus 7 to the power of 5. This equals, let's see, 3 to the power over 10 to the power of 5, which is 243 over 1,000. 1,000, nope, 10,000. 100,000, sorry. So this is my limit of this function. So I needed to make sure that my inside function was continuous. It was everywhere. So my inside function raised to the power of 5 was also continuous because of my theorem here. And then because it was continuous, I could simply plug in the point x equals 1. Next, we're going to move on to composite functions. So if I have g of x is continuous and f of x is continuous at the point g of a, then I have the following. This is going to look a little bit funky, but we're going to do some examples. I have the limit as x approaches a of f of g of x, this is our composite function, is equal to f of the limit as x approaches a of g of x. And if the limit as x goes to a of g of x is equal to L, and f of x is continuous at this point L, then the limit as x approaches a of f of g of x is equal to the same thing, f of the limit as x goes to a of g of x. So even if g of x isn't continuous, right, so here this is saying that even if g is not continuous at a, but my limit is equal to a number, as long as f is continuous there, I can take the limit like this. So the difference between part A and part B of this theorem is in A we are assuming that g is continuous, and in B we are assuming that g is possibly not continuous at the point A, but it does have a limit as it approaches A. So let's use this theorem to evaluate the following limits. My first one is the limit as x approaches -1 of the square root of 2x squared minus 1. Now, I know some of us have taken calculus before, so you might just be like, oh, we can just plug in -1. And we'll get there, but right now we don't know, technically, how to evaluate a square root function. But we do have the above theorem, and I can write the square root of 2x squared minus 1 as a composite function. So I'm going to rewrite the square root of 2x squared minus 1 as f of g of x. My outside function would be f of x equals square root of x, and my inner function would be 2x squared minus 1. So this is how I write this as a composition of functions. So I need to make sure that g of x is continuous. Well, that is true. This function is continuous. It's a polynomial. So g of x is continuous at the point x equals -1. So we're good there. Now I need to make sure that f of x is continuous at g of a. In this case, g of -1. Well, I see that g of -1 is equal to 2 times -1 squared minus 1, which is equal to 1. So this means that f is continuous at g of -1. So we've taken care of what we need to make sure is true, and now I can use the theorem itself, this guy right here. So the limit as x approaches -1 of the square root of 2x squared minus 1 is equal to f of the limit as x approaches a of g of x. Well, f here is the square root. So that's f of the limit as x approaches -1 of g of -1, which is 2 times -1 squared minus 1. So this is the square root of, well, the limit as x goes to -1 of this function is just 1. So my answer is 1. So I had to first decompose my function into composite parts, f and g, my inner function and outer function. Then I had to make sure that g of x was continuous at x equals -1. We found that it was. It's just a polynomial. And then I had to evaluate g of -1 to make sure that f was continuous there, and it is. So then I used this theorem up here in order to take f of the limit as x goes to -1 of my function g of x, and I got 1 as my answer. Let's try another example. Actually, I'd like for you to pause this video and see if you can do this one by yourself. I'm going to give you a hint. Try to factor the top of this rational function and see if something cancels out. Go ahead and give it a try, part B. All right, hopefully you've tried part B. So I need to first decompose my function into two parts, my inner function and my outer function. So my inner function is, g of x is x squared minus 4 over x minus 2. And my outer function, f of x, is equal to cosine x. So g is not continuous at the point x equals 2, because if I plug in 2 here, it makes my denominator equal to 0. So I'm going to say g of x is not continuous at the point x equals 2. So I can't use part A of the theorem above. Let's see if I have a limit at the point at x equals 2 though. So, but the limit as x goes to 2 of x squared minus 4 over x minus 2. Well, this is the limit as x goes to 2. The top factors as x plus 2 times x minus 2 over x minus 2. My x minus 2's cancel out. And I plug in x equals 2 and I get 4. So my limit does exist at the point x equals 2, even though g is not continuous there. So I use part B of this theorem. Even though I'm not continuous at the point x equals 2, I still have a limit. So by part B of the theorem, I have the limit as x approaches 2 of cosine of x squared minus 4 over x minus 2 is equal to, we didn't check that f was continuous at L, but I can take the cosine of anything, so f is continuous at L, that's fine. So this is equal to the cosine, that's my f function, the cosine of the limit as x goes to 2 of x squared minus 4 over x minus 2. We've already solved for this portion. It was equal to 4. So this just equals cosine of 4. You might be saying, but Amanda, can't we just plug in x equals 2 in here? And it's okay because our x minus 2 cancels out on the top and the bottom? Well, again, we don't know yet that we can just plug in x equals 2 into my function yet. We'll learn that later. But for now, this is what we have to do. We have to decompose our function like this and use this theorem. All right, we have a couple more things in this lesson. We've talked about continuity, and now we're going to talk about what it means to be continuous at an endpoint. So we say a function f of x is continuous from the right at the point A if the limit as x approaches a from the right of f of x equals f of a. So we can be continuous from only one side. What does this look like? Well, if I had a function that looked like this, for example, if this is a, then this would be right continuous, continuous from right, since the limit as x goes to a from the right of my function is the function evaluated at that point. And f of x is continuous from the left at the point A if the limit as x approaches a from the left of f of x equals f of a. This would look something like this. If this was a. So my limit as I approach a from the left is that function evaluated at that point. If I am continuous on every point inside an interval, continuous at all points in an interval, then I am continuous on this interval if I am continuous from the left and the right at the endpoints. So as long as I am continuous at all points inside an interval I, if I have endpoints, then I have to be continuous from the left or from the right at the endpoints. I wouldn't worry so much about this definition, it's pretty obscure, but we do have to check endpoints. That is what this definition is reminding us. So example 5 wants us to determine the intervals of continuity for f of x. So we have two pieces here, it's a piecewise function. Both of them are polynomials though. So because they're both polynomials, they are continuous for everywhere except possibly at this point 0. So both pieces are polynomials So they are continuous for all x not equal to 0. The only reason my 0 is a sour point is because I changed there. So now I need to check what's going on at x equals 0. So I see that the limit as x approaches 0 from the left. So if I approach 0 from the left, actually, you know what, let's draw this function real quick. So for x less than or equal to 0, I have x squared plus 1. So something like this. I have a closed circle there since I can be equal to 0 on this board. And then greater than 0, I am at 3x plus 5. So something like this. You can see pretty clearly that I am not continuous at the point 0, right? So my left-handed limit, though, looks like it is continuous at the point 0. So because the limit as x goes to 0 from the left at f of x, we are on the quadratic portion. This is the limit as x approaches 0 from the left. Whoops, from the left of x squared plus 1, which is equal to 1, and this is f of 0. So according to this definition right here, I am continuous from the left. So f of x is left continuous. But the limit as x approaches 0 from the right, now we're on the linear portion of f of x, is equal to the limit as x approaches 0 from the right of my linear portion, which is 3x plus 5. This limit equals 5, which is not f of 0. f of 0 is 1. So f of x is not right continuous. So my intervals of continuity are everywhere to the left of 0, including the point 0. So I write that as negative infinity to 0. And because I'm going from the left, I include the point 0 using a bracket since I am continuous at the point 0 from the left. And then I'm not continuous at 0 on the right, so I put a parenthesis there, 0 to infinity. So this is how I write it. This is where I am continuous. Negative infinity to 0, including 0 from the left, and 0 to infinity, not including 0 on the right. Now we have a theorem of continuity of functions with roots. So I assume that n is a positive integer, and if n is an odd integer, then I have the following. F of x to the power of 1 over n, this is the nth root, is continuous wherever f is continuous, since I can take any odd root anywhere, including negative numbers. Wherever f is continuous. Taking odd roots is fine, but taking even roots is a little bit trickier, right? Taking the square root means that I have to have a positive number on the inside of the square root. So f of x to the power of 1 over n, if n is even, is continuous wherever f is continuous and positive. So I can take roots of functions and guarantee their continuity as long as f is continuous, and if n is even, then f also has to be positive, since I can't take the even root of a negative number. All right, it looks like we're done, but actually we have one more theorem that failed to make it onto the notes. This is a pretty important theorem though. So let's write this out. Theorem. It's called the intermediate value theorem. And it says the following. Suppose f of x is continuous on the interval a to b closed interval a to b, and L is a number strictly between f of a and f of b. So it cannot equal f of a or f of b. Then, what this theorem says, there exists at least one number we call it C, in the interval, open interval, a to b, such that f of c is equal to L. Wow, this is a lot. Suppose f of x is continuous on the interval from a to b, and L is a number strictly between f of a and f of b. Then there exists at least one number c between a and b, such that f of c is equal to L. What does this look like? Let's draw some pictures. So, I need f of x to be continuous. So let's draw our simplest form of a continuous function, a linear function. So we're going to draw this linear function here. I'm going to call this a and this b, which makes this f of a and this f of b. Okay, so I have a continuous function. I have a, I have b, I have f of a, and I have f of b. So what the intermediate value theorem says is that I can pick any number, any y value, between f of a and f of b, so anywhere between these two things, strictly between f of a and f of b, so I can't actually equal f of a or f of b. But say I pick, I'm trying to erase this, hold on. Say I pick this point here. Because this is strictly between f of a and f of b, I am guaranteed to have a point C here such that f of c equals this number L. That is what this intermediate value theorem says. If I pick any number strictly between f of a and f of b, then there is a x value between a and b such that the function evaluated at that x value equals L. Say I had a funkier looking function. So maybe I have a function that looks like this. Okay, so we're going to call this A, and we're going to call this B. Actually, you know what? Let's make it a little bit different. It's a little too hard. All right, so here we go. Okay, so now we're going to call this B and this A, which makes this f of A and this f of b. So again, I can pick any number strictly between f of a and f of b, anywhere in here, and I can guarantee that there is a point between a and b such that f evaluated at that point is this number L. So I'm going to pick this point, and I can see here that there are actually multiple places that f is equal to this function. So if I just draw a line like this, right, I see that here, 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 and here, they satisfy the mean value theorem. So maybe I'll call this one C1, this one C2, this one C3, C4, C5, C6, and C7. So in this case, there are multiple C values that satisfy this. The intermediate value theorem guarantees at least one, but of course we can have more than one, as this example shows. So this is what the intermediate value theorem says. It's pretty handy in some situations. And that is the last thing that we are going over today. So that's it for today. Hope you have a great weekend. And if you have questions about this lecture, please post them on the discussion board on Canvas. I will see you on Monday.